Hello, everyone. I hope everyone's doing okay in these troubling times. Today, we're going to be talking about energy dispersive spectroscopy of X-rays. So it's a technique used both in SEM and in TEM. So today, we're going to be covering sort of what is EDS, also the components of the EDS detection system, how X-rays are produced and the nature of the X-rays. We're going to talk about the SEM settings that we use for doing EDS, and within the EDS system itself, what settings we use in the software in order to get the results that we want. So, and we'll also talk about EDS resolution, some things about sample preparation, and I'll give a few examples. I'll try to leave enough time that we can get in plenty of questions if needed. You can see here a nice picture showing some EDS mapping, and we're seeing different elements, and it's a mixed map, so we can see the different colors. So it's orange because there's a mixture of red and yellow. So what is EDS? So there are common acronyms that are used for EDS, such as EDS, which we've been saying, which I'll use for most of the presentation. And a fewer number of people refer to it as XEDS. It identifies the chemical elements present within a specific sort of volume. We don't get any valence state information that you do with some other techniques. It is non-destructive, but because of electron beam energies that are involved here, it may cause damage to certain samples or cause contamination, such as carbon deposition. It can be both qualitative and quantitative. And as I said previously, it's both an SEM and a TEM technique. In the case of doing maps and line scans, it's a scanning transmission electron microscopy technique. So that's why we have the S there in the description. The sort of data that you normally get out are spectra, which can be from spots or areas, maps, or line scans. Because of the nature of X-ray production, we don't get any detection of hydrogen or helium. Lithium, you need to have the right type of equipment to do that and conditions. EDS doesn't require any special preparation beyond what you normally have to do with either SEM or TM. But you do need to be more careful about preparation when you're doing quantitative analysis. So EDS detectors, there are two main types that we see. There's a silicon lithium detector, which is cooled with liquid nitrogen. You can see down here in the bottom right-hand corner, that type of detector. One thing I will mention at this point, we pretty well have exclusively Oxford Instruments EDS systems, so it's going to tend to be a lot focused on that particular type of system. But we can talk about the other systems that do exist out there. So up here you can see the second type of detector, which is a silicon drift detector. It has a Peltier cooling unit, so it's thermal electrically cooled. And next you can see a picture which is showing you the sort of composition of the tip down at the bottom, where you have the different components of the EDS detector. So there's a columnator, which is used for sort of focusing, collecting the X-rays. Because we don't want the electrons going into the actual sensor, we have an electron trap so that the backscattered electrons especially don't get into the actual detector. Now, the windows that are in front of the detector can come in various types. Mostly these days you'll see probably polymer windows, but they're not like a big open piece of polymer. You'll see that they'll have slits in them where you have a coating over the polymer and you'll have the slits through which the X-rays can go. There also exist out there thin silicon nitride windows as well. And on very old systems, you'll see beryllium windows. The big disadvantage with these systems is that you can only, with a beryllium window, detect heavier elements such as sodium and above with the EDS detector. There are also versions of detectors that have turrets on them, which allow you to switch between sort of windowless and having a thin window. There also are detectors that are strictly windowless, which don't have anything between the vacuum of the microscope and the sensor itself. Back in behind the sensor. So for the most part, sensors these days are silicon. There are a few detectors out there that actually are germanium, but those are kind of, I haven't seen anyone that actually has one of those, but they do exist. And behind that, we have a field effect transmitter, which is used for sort of some of the amplification that needs to be going into the system once it goes out into our pulse processor and analyzer systems. So we'll have a computer associated with EDS, and we'll have EDS software for doing things. Now, when the electron beam hits a material, and in this case, we're talking about a bulk material. If we were talking about TEM, we'd maybe be talking about a thickness of material up in this sort of range here, where you see sort of the secondary electrons coming from. So the nature of X-rays is that once they go in here and they get produced within the material, they travel in straight lines. They're electrically neutral, so electric and magnetic fields don't have any influence on them. They're produced at high voltages, so you need to have sort of in the kV range to produce X-rays of significant energy. The behavior of the X-rays is controlled by the nature of the material that you're looking at. And the X-rays, there's sort of three possible interactions you can have. You can have absorption, where the X-ray gets absorbed by the material. Dispersion, where you're getting the X-rays either deflected or actually creating new X-rays. Or transmission, where they travel through things. Now, when we're talking about the actual production of X-rays, if we have on the SEM an accelerating voltage of 15 kV, we're going to produce 15 keV electrons. The kV and material affect the depth to which the electrons of the primary beam or electron beam penetrate. And the range of X-ray energies that are produced once the beam interacts with the specimen is basically from sort of 0 to the energy of the electron beam. So 15 kV in this case. Now we can have different types of X-rays produced. So here you're seeing the sort of volume where we're getting the characteristic X-rays, which are the X-rays which give us the peaks, which allow us to identify elements. Continuum X-rays come from this sort of volume. And those are the X-rays that are associated with a sort of background radiation or breaking radiation. And you can have the X-rays that are produced by either the characteristic or background produce other X-rays, which can come from sort of this region. So it's important to talk about what actual sort of data we're collecting. So it's important to understand where the X-rays actually come from and what controls their sort of energy. So here we have an atom of silicon, and if we have the primary beam knocking off a secondary electron, we get an X-ray produced when a higher energy shell electron drops to a lower energy shell. So EDS uses these inner shells, so the K, L, and M shells, removing electron from the K shell, the sort of requires the highest ionization energy. For every element, each shell and subshell have specific ionization energies. The higher the atomic number of material, the higher the ionization energy for a given X-ray shell. So characteristic X-rays are produced with these various transitions. And here you can see if you're having the electron dropping back down to the K shell where we've had our secondary electron produced, there's a certain energy that's produced of the X-rays. So background radiation, or continuum X-rays, or a fairly unpronounceable German name for breaking radiation, is produced when the electrons are affected by the nucleus of the atom, but don't cause any electrons to be lost from the atom. So because this is an inelastic collision, some energy is lost, and some of that energy is converted to X-rays. It is possible for all the energy to be lost. So the energy range of these X-rays that are produced can vary anywhere from almost 0 eV up to the energy of the primary beam. And here you can see what the background radiation looks like when we're looking at a spectrum of X-ray intensity versus X-ray energy. The Duane-Hunt limit is basically the accelerating voltage electrons that are produced here. So if we're doing 15 kV, that's our Duane-Hunt limit. So 15 kV is the Duane-Hunt limit for the X-rays produced. One problem we have is the very low energy background X-rays tend to be absorbed within the sample or within the detector itself. So we don't see them as much. Now we're talking about the actual production of what we actually see. If we're considering, say, silicon, we'll have different shells that can be, we can ionize. So once we ionize an electron, and we get a secondary electron produced, an electron from a higher energy state shell can drop down, and we get an X-ray produced. So in this case, you can see the energies of the various X-rays produced. So in this case, this is the most common X-ray you see with silicon. So 1.74 is the energy of the actual X-ray, and you'll see that on your spectrum down here. And here you can see the nice background radiation here, and you can see the characteristic X-rays sticking up as peaks. So one of the problems with doing this type of spectroscopy is you do get some of the X-rays absorbed. They don't actually manage to get out of the sample. Sometimes you have a lot of surface roughness. This can be sometimes a problem because the higher areas will absorb the X-rays that are in the sort of path to the detector. So higher atomic numbers tend to absorb the lower energy X-rays, so we have a lot of problems with fairly light elements. Also, if there's a very long path for the X-rays to travel through the material, it's more likely that the X-ray will get absorbed. Now, another thing that can happen is once we produce these X-rays, they can produce secondary or scatter X-rays with different sort of characteristics from the X-ray that was produced by the original element. This is likely to happen if the X-ray energy is equivalent to the critical ionization energy of an electron in another element. Light elements tend to have very low ionization, and they also have low sort of fluorescence yields. So we don't have it fluorescing and creating more X-rays. Now, one other thing that you have to consider sometimes if you're looking at X-ray efficiency is that there's a competing process to producing X-rays, and that is Auger electron production. So Auger electron production is more likely to occur in low atomic number materials. So we have to consider that as well. So here we have an illustration showing that we can get Auger electrons instead. Now the primary electron beam will have you'll set the energy of that by using the accelerating voltage, or kV. Now, the energy of the electrons in the primary beam must be high enough to overcome the ionization energy of the specific element that you're looking at within the material, and of the particular inner shell electron. So this is the critical ionization energy. Now, because of the kVs that TEMs are set to, this usually isn't a problem for them. So it's mainly a concern in SEMs, or if you're doing TEM in the SEM. So if we don't achieve the critical ionization energy, you don't get any X-rays produced, or if you don't have enough energy above this value, you may not get a large number of them. So here we can see in the top spectra, the main sort of K alpha and K beta peaks for the, so that's the K shell peaks for chromium. And down here we can see the L shell peak for chromium. So at 15 kV, we have enough, the primary beam electrons, high enough energy, 15 above, you can see the energy of the X-rays produced here. So we have enough energy, and so we're getting all these X-rays produced. However, if we drop down to 5 kV, you can see here that we don't actually get any peaks here. And you can also see it has an effect on the background radiation, that we're only getting, 5 kV sort of background radiation. Now, what's important here is you have to have enough voltage to get enough stimulation of the X-rays within a material. And usually, if you're looking at X-ray production versus the voltage, the magic optimal number ends up being 2.7. So you want to have it above 1 times that energy so that you just don't get a few X-rays. So usually we're trying to get in the region of 2 times the voltage in order to stimulate the X-rays. And here you can see where we've done, if we do some understimulation. So at 25 kV, both the silicon and copper peaks are well stimulated. But at 15 kV, there's a reduction in the amount of X-rays you get for copper. So copper is around 8 kV. So we may want to go a little bit higher to get sort of proper stimulation. So that has to be considered as a very important factor in looking at things. So you have to get the kV at a value that's high enough. Now, the beam current or spot size or probe current has to be stable during EDS acquisition. This is especially important if you're doing quantitative work. The current represents the number of electrons in the primary beam. It's controlled by the condenser lens or spot size control. The number of electrons in the primary beam are proportional to the number of X-rays produced. So basically, more current, you will get more X-ray counts. So here you can see same kV, 15 kV. We're getting more X-ray counts at 3.2 nanoamps as opposed to 0.8 nanoamps. Increasing the beam current will not change the relative heights of peaks. So the different tungsten peaks will still have the same sort of relative heights to each other within the material. I'm going to talk about dead time in a moment. We'll talk about a few factors first. Once the X-rays have escaped the sample, they need to get to the detector. So you have the detector up here. There's a particular takeoff angle that it's set to. We have the sample here. So there'll be a particular working distance. And for every EDS arrangement, there is a set working distance where you have the proper takeoff angle for collecting X-rays, and it's calibrated under those conditions. So any variation from that, so closer working distance or further working distance or a different angle, will have an effect on what you're actually collecting. So tilting the sample, unless it's been calibrated for tilting the sample, may have an effect. Also tilting the sample, we run into sometimes the danger of backscatter electrons hitting the detector because they're fairly high energy. And we want to have that sort of consideration of that. So you can see here, this is at a working distance of 4 millimeters. We have 100,000 X-ray counts, whereas if we drop down to 10 millimeters, we have 35,000 X-ray counts. So the number of X-rays counted. In this particular detector arrangement, 4 millimeters is the working distance that's been set for the system. You will find on a lot of other systems it is actually 10 millimeters. Now, it's still getting a lot of X-rays, but that angle may not be optimum for doing quantitative work. Now, one thing that's important is that once the signal leaves the detector, it goes to the pulse processor. And we need to adjust the amount of time that we're processing the signal. So this is actually an averaging of things. So here you can see a nice chart that shows us sort of the different sort of pulse processing times, or as they're called, process times. And it's not a set time. You see it's numbered basically from 1 to 6. So longer processing times, we get better resolution of peaks because they're averaged longer. It also improves our resolution, but we get a higher dead time. Dead time is the time when the system is not counting the incoming X-rays, but is processing the previous collected data. 28 to 50% is a reasonable dead time. You don't want to have less than 10 because you really don't have saturation of the detector with signal. And above 60%, especially with older detectors, you will run into some problems with artifacts. It also will, with the newer detectors, you'll also start to see some artifacts. it also takes much longer to collect if you do. The X-ray resolution that we actually get is dependent on the detector and its electronics, plus, as you can see, the process time that we use. Now, the counts of X-rays, or X-ray intensity, you'll also see it sometimes listed as counts per second, is affected by the working distance, which would be set for the particular EDS setup, KV, current, and also the detector size. So there are a range of detector sizes. In something like a tabletop SEM, you might have a quite small detector. There are now quite large detectors available. And on some systems, like actually the one that we're using for a lot of these examples, it actually has two 80 millimeter squared detectors. So when we're talking about the sort of peak height here, you shouldn't make the assumption when we're doing SEM that it's proportional to the concentration of the element. There is a tendency to do that. So you do tend to have more of something if it tends to be a larger peak. But if you can look here, when we went down here to a lower KV, we're getting more contribution from the carbon that's present on the surface as a coating, or the carbon that's within the material. So it does have a much taller peak. And so you can't really go by peak height. It is related. So the concentration of elements is related to the peak height, but you have to be careful about making conclusions about them. We do get spectral artifacts. One thing that's nice about modern detector systems is that a lot of these are corrected for. However, if you look up in the two spectra that we have up here, you can see here's some, in this case, we have some escape peaks. And this case is with it uncorrected. It's not 100% corrected by the system. So this is an older system. There has been some improvement in the newer system. So internal fluorescence usually only happens in the older detector systems, which are the silicon lithium. Escape peaks happen when you get the actual X-ray not being converted to an electron hole pair in the actual detector or sensor. Instead, you get a silicon X-ray generated. So, but because for all the sort of elements within the material in the that are detected, you can actually correct for that. So usually in the older systems, you may be able to click on a button which will do the correction. Newer systems usually do it automatically, along with pulse processing. Some peaks also, the newer software corrects. You'll usually see it referred to as pulse pileup correction. This happens when you get two X-rays coming in simultaneously into the X-ray detector, and it records one X-ray energy signal with both energies. So it could be the same X-ray, or it could be two different energy X-rays that do this. Higher count rates, so sometimes you see this on the TEM, or if you have the dead time above 60, you will get more prevalence of the escape in some peaks. And sometimes it will have problems at correcting for those. I have seen where it does do overcorrection. So something to look out for. when you're doing things. Another thing I will point out at this time, EDS detectors do detect infrared energy. So if you do have the chamber scope on, you may get a very high dead time because of that, and you will get a very strange looking X-ray spectra. So when we're talking about the spatial resolution, so sort of basically the area over which we're getting the X-ray information, and the depth, there's a little variation between SEM and TEM. There also are some detection limits. So with SEM, you're usually looking at spatial resolutions and depth resolutions from, maybe with high atomic number materials, maybe down to 0.2 microns up to, a few microns, but usually it's never more than sort of 10 microns in most cases. So it's usually on average a few microns. Unfortunately, in low vacuum and environmental SEM, we get a sort of skirting effect where the spatial resolution actually gets significantly expanded. So instead of the spot size of the sort of X-rays being, a few microns, it may end up being, 50 or more microns. So it's something you have to be careful about when doing SEM work. In the TEM, we have the great advantage of it's very thin. So we're not going to have as much volume. Also, because we have higher KVs, we're not getting as much beam spread. So we're getting spatial resolution on the order of nanometers, and the depth is basically the thickness of the sample. The detection limits are usually around 0.1 weight percent, a little bit higher for lower atomic number elements. Beryllium, you may have some problems unless it's there in significant quantities. Same with boron. Detection limits for TM tend to be a little bit better. It is possible to get sort of trace element analysis sometimes. Detection limits are approximately the peak height equal to 3 times the standard deviation of the background. So if you have a very noisy background, you're going to run into sort of more problems. So this is why longer collection times are better for having better detection limits. And you can have different variations based on the X-ray lines, what sort of elements are around. So you will have different problems with the light element in heavy elements. So that can be an effect on things. Accuracy will really depend on sort of what sort of spectral processing you're doing and corrections to the raw data. And I'm not going to talk about it a lot, but you can use standards to actually improve quantitative detection of elements. Reproducibility is basically based on, the statistics involved in things. More X-rays, you have a more reproducible data set. Sample preparation, you have to consider things like size. Can you fit it in so you can look at the regions of interest? Can you go to the working distance? You don't want it moving around. You want to have it conductive. So you want to have a pathway to ground. Quite often carbon is the preferred coating for EDS. We have to worry about what effect sort of heavier metal coatings have on absorption of sort of low energy X-rays. Carbon, though, can cause problems if you don't also correct for it. So there is a correction you can use for coatings. Not always great for doing the heavy metal ones, though. You have to make sure your sample is representative. So you don't want to alter it with something like etching and actually remove material or form oxides on the surface. Clean, you want to have the organics removed. You don't want to be able to see any sort of fingerprints. I have seen people analyze things, and I had to tell them afterwards that you analyzed fingerprints, not anything on your sample. You also have to be careful about the solvents you use sometimes. Acetone has a tendency to sort of redeposit some things, so sometimes you're better to use a higher quality solvent for cleaning things. Carbon, unfortunately, pretty well everything on the planet will have carbon on it. And also the vacuum systems you have within SEMs and TMs are not perfect. So you can quite often detect carbon, even though there is absolutely no carbon supposed to be in the sample. You can do things to improve this. Sometimes you might plasma clean the sample. It's something that's quite often done in the TEM. Biological material, because we are looking at pretty well everything with EDS. We have to, in order to avoid sort of charging or change of structure effects, we need to make sure it's dehydrated if we're doing high vacuum sort of work. But, you know, there are circumstances where you can do low vacuum or ESEM of biological materials. One thing that's sometimes used now is conductive liquids. Also, we need to kill off usually the biological material, so we might have to fix it and sort of attach it to sort of surfaces. Conductive staining is sometimes used, so we might be adding a heavy metal to things like osmium, or we might be doing labeling of things like with gold nanoparticles. So, and we may be looking at EDS for actually where these things have stained or where the labeling is to identify sort of structures. Now, when we're talking about quantitative analysis, we want to make sure that the sample is polished flat. And the polish, depending on what sort of accuracy you need, might have to be down to the sort of 50 nanometer root mean squared surface conditions. So you might have to have an extremely fine polish to really get good quality quantitative analysis. Now, we have been talking about qualitative, which is basically where we're just identifying the elements with the characteristic X-rays. So there's all the peaks that are there. One thing to always do is to not accept what the software is telling you. Identification of elements is not 100% accurate. Elements can be missed or incorrectly identified. You will have more problems, usually the broader the peaks are. So if you do have very low process time, that's sometimes you get more problems. Also, there is a problem sometimes with peak overlap. So there are certain peaks from different elements that do overlap. So we sometimes have problems differentiating between those elements, or a particular element might get buried under another peak. So usually if you're doing qualitative EDS, but you are looking at something that's unknown, you want to start maybe in the 15 to 20 kV range so that you have enough overvoltage for most sort of X-rays that are produced. You should do it before you do quantitative EDS, just so you have a good idea of what actually is going on. Quantitative EDS results in, you can get sort of mass fractions or weight percent of the elements present in the sample. The spectra are processed, they remove the background X-rays, spectral artifacts, and then they're compared with some data that's been measured, usually from the factory of the EDS manufacturer off reference materials. And those are used to actually determine what the quantitative results are. This is referred to as standardless quantitative analysis. Some people also refer to it as semi-quantitative analysis. Excuse me. So, which I would say now with more sort of better software and detectors, we're really, I think on the older systems, you could maybe say that it was semi-quantitative, but I think there's been quite a lot of improvement in what you can do, that we can say that it's a quantitative analysis now. You can improve the quantitative analysis if you actually collect data from standards of similar composition on the same instrument. So this can improve accuracy quite a bit. But when you are doing quantitative analysis, how homogeneous the material is and its density and its topography will have significant effects on the analysis results. So here we can see some EDS spectra. And along with this, we've also done some quantitative analysis. So we can see all the various nice peaks. So we have X-ray intensity. So here it's in counts per second per electron volt. You could also list it as counts as well. So you can see your background, the nice little whale, as it were, of the background radiation. And we've done it with normalization, the quantification. So we've actually forced it to add up to 100% for what's here. So, but some things that I will point out. So in the first spectrum here, this has been identified by the computer as phosphorus. It is actually not phosphorus. It's actually one of the peaks from tungsten. It is also identified that strontium is present. Strontium is not present in this sample, even though it gives us saying there's 2% strontium. There's actually no strontium present. Usually you can confirm things like that by looking at other peaks that are supposed to show up for strontium. Now, sometimes you will run into the problem that due to the sort of sizing of the spectrum, it doesn't label all the peaks and things, even though you've asked it to. That happens. So down here, we've properly labeled the peak and we've got rid of the strontium peak. And you can see here that we have a profile for what the tungsten peaks, their position, and also their relative height that normally exists. Sometimes the relative height will be affected if we're looking at sometimes single crystal materials. So that's something you have to be careful of sometimes. And here I've blown up what the quant is so that you can sort of see it as rather than just squint your eyes on thing down here. Oh, and also it didn't identify the iron here, and we can see there's some iron. Now, we don't have to do the quantitative analysis normalized. Usually, if we're going to be doing quantitative analysis where we're not doing normalization, we want to make sure that we optimize the spectrometer. Usually, we use a calibration element. The calibration for the spectrometer itself, usually the companies use manganese. I quite often use cobalt. In the case of optimization, it's usually an element that's convenient to use. So depending on the energy range, we'll use things like copper tape or a piece of silicon wafer for that. So why I'm showing this is you can see that we're not adding up to exactly 100% here for the quantification. Also, we're running into an absorption problem here. The absorption problem is the fact that we have assumed that the carbon coating is 10 nanometers, and we've corrected based on that. But in fact, the true value of the carbon coating on the sample is closer to 90 meters. So we are getting a significant error in the data for light elements, and then in this case, we're talking about oxygen, compared to what we know as the certified values for the mineral that we're analyzing, olivine. So you can see if we have the 10 nanometer assumption, this is the sort of results we get with quantitative. And here, closer to the actual values, manganese is off a bit. We may have to do, we may not have properly corrected for sort of matrix effects. So we may have to do some standardization to actually improve the sort of numbers that we're getting for maybe the manganese in this case. Charging. So a lot of people make the assumption, because X-rays don't have any sort of effect of charging, that charging isn't a problem. But charging does affect the primary beam. So here we can see an example of using a 15 kV accelerating voltage. And you can see down here on our spectrum that we are not getting background X-rays above, really very much above 9 kV. So we have actually decelerated the beam due to charging, and that is having an effect on what we're looking at. So we're maybe, have a 9 to 10 kV beam actually hitting the sample and producing X-rays. So that means that these peaks that we're looking at for iron are not optimal. So we may be getting an incorrect number for iron. Now, another thing to consider, if we look at the actual sample, is that this is not a fully dense material. Lots of holes. There's also lots of topography. So we're going to get some shadowing and areas where we don't get X-rays. So this is not 100% dense. It's fairly rough, the surface. So that's going to have an effect on our quantitative analysis. So we may have to do something like crushing up the material into powder and pressing a pellet to get a better reading of sort of the composition of the material. So here we might have to sort of coat it some more. It already does have a carbon coating on it. We might have to improve the conductivity, maybe painting closer to the area of interest, using low vacuum or SEM, but at the cost of spatial resolution. Mapping, something a lot of people like to do, gives you nice colored pictures of things. You can assign different colors to different things. So what we're looking at here is sort of the X-ray counts or concentration of one element and a particular shell of X-rays over the area of the sample. So we could do a smaller area. Here we're doing the sort of full field of view that we're doing. You don't want to do mapping usually at fairly low magnifications. We run into problems with sometimes some SEMs will have distortions. Also, we run into geometric problems just based on sometimes you get sample curvature and issues like that. So usually don't want to go much lower than 50 times, but you may have some issues with your particular SEM. So, you know, ask about what sort of magnification should sort of be the minimum. Now, when we're talking about maximum, you have to keep in mind this sort of spatial resolution of things. So there's no point going to 50,000 times in the SEM. You're going to have a lot of overlap of data. So, you know, that's not really the best thing to do. So when we're collecting maps, we're doing specific time per pixel. We may have to limit it if we're having sort of a charging problem. We'll do a certain number of frames, so collection of the full field of the field of view multiple times, so scanning it. And when we're actually collecting this data, if you look down here on the spectrum, we're using an energy window to determine what are the particular number of counts of X-rays for that particular element, and from that calculating any sort of concentration as well. Now, this can sometimes be a problem based on what kV you're using. In this case, we're using enough energy. We're using 15 kV, so nickel should be properly optimal. So we should be getting good counts there. Line scans, very useful thing. It doesn't take the time you have to do for a map. So maps you can, you know, might be doing if you got a really modern system over a very short period of time, but sometimes mapping might be done up to, you know, tens of minutes, hours, depending on how much data you need and what sort of things you're looking at in the map, especially if you're looking at things that are fairly low concentration. You're going to have to do longer scans with line scans and maps. So it's important to sort of consider what sort of information you need, whether a map will get you the sort of information you want, or whether a line scan, which takes less time, would be more beneficial. So same thing, X-ray counts and concentration. The line actually represents a number of data points, so you can set how many data points you're going to be doing, or the distance between data points, which you can sort of keep in mind what might be your sort of spatial resolution. So you'll have specific dwell times, so amount of time per point, how many times you scan the line. We use energy windows like we do for mapping. Now here, instead of doing sort of the counts of X-rays like we did in the map, I've actually converted to atomic percent. So we can sort of have an idea more of what we're actually looking at. So, and here you can see there's a fairly high atomic percent of carbon. This isn't because of the coating. This is because this material is actually a carbide material. So there is a lot of carbon in it. So may not have been so obvious in maybe some of the previous analysis, but here you can see that. And you can see the nice distribution over the distance. So here we see in microns versus atomic percent, how it is across the line. Now, this has also been processed a bit, so there's been some smoothing. We've also done what's called binning and combined some pixels or data points, as it were, in this material. So coming to the end here, so we'll probably stay a little bit over time to do some questions. Just going to mention that there's a lot of other processing you can do with things. So the map that I showed originally, we've actually overlaid the different X-ray maps. So the blue tungsten, the yellow chromium, and the red nickel, which, because there's lots of chromium, it's orange here. And you can see also the SEM image underneath as well. So we've basically mixed the images there. But there are various other things you can do within software. The more modern the software, the more things you can do. So corrections for coatings, like I showed you in the one example. Correction of spectral artifacts, which we talked about. You can also do some background subtraction or subtract or look at the differences between spectrums, things like that. You can do spectral processing for correcting for overlapping peaks. There's other sort of image processing and analysis you can do. Labeling, important to label things. So it would be useful to label the actual elements here and maybe put a little chart as to what they are. We can also use other programs for doing things. So you might export your data out and do things. Or you might do some simulations, Monte Carlo simulations, to figure out sort of where you're actually collecting the X-rays from to actually do something. So two things I will point out. Goldstein's sort of the Bible of scanning electron microscopy and microanalysis. The Australian MyScope website is extremely good. I've used that for a lot of the source material, so thank you to them. I would also like to put a thanks out to Richard McLaughlin from one of the EDS companies that actually produces the Aztec software. There's a lot of help and advice and things like that. So the casino website, so if you do want to actually do some calculations, NIST down in the States produces a program that's very useful. You may have to have some good information about the SEM for doing things like that and TEM before you can really make full sort of utilization of the program. But it's very useful. Also, the people at NIST are very helpful as well for questions there. So, come to the end here. So, thank you for joining us. And please ask some questions. Now, you can also send me an email at butcher@mcmaster.ca. I am willing to answer questions, industry or academia or general interest. No problem answering questions about topics. Okay, so let's have some questions.
Great, thanks, Chris. So any questions, please put them in the chat. So first question we have, if we are trying to get accurate quantitative analysis, do we need to worry about XAF corrections, or does modern software technology take care of it well enough that it's no longer a concern?
Yeah, it is internalized, but XAF, so on some systems, it will allow you to switch between different systems of correction. We actually don't use XAF corrections anymore. There's a different model that's used, but it's been improved somewhat. So it is better corrected, but you're still dealing with, if you're doing standardless, not doing corrections for matrix effects. So for instance, if you're doing standardless on our systems, which are from Oxford Instruments, the corrections for silicon are based on running a standard of silicon dioxide, which is not the same material as silicon. I don't know why they didn't use silicon. The correction for oxygen is based on the standard of silicon dioxide as well. So it does create errors. So polishing is really critically important for getting a nice surface, and angle also does have an effect, and you have to be at the optimum position.
Great. Next
question.
question. You mentioned that hydrogen and helium could be detected by EDS. Could you elaborate more on that?
You just don't get X-rays. They're too tightly bonded, the electrons, so, and you're not getting any X-rays produced. They have no outer shell electrons to drop down to the inner shell. So there's no X-rays produced. We have to have that, as it were, knocking off the secondary and that dropping down or relaxation of the electron structure of the atom in order to get X-rays produced.
I guess on a similar note, and you sort of just answered this, but at the beginning of the lecture, you said that lithium can be detected with the right equipment and conditions. What do you mean? Can you please explain more?
Okay, so lithium is a very low energy X-ray. So in systems where you have windows, the X-rays from lithium are basically don't get to the detector. So you have to have a windowless system. You also have to have the resolution of the spectrometer. So you might have to have a specific spectrometer that has high resolution in order to collect the lithium. Also, lithium is something that electron beams can sometimes cause migration of or loss. You can actually evaporate a lithium in the TEM. So you have to be careful with the electron beam on things. So you have to have proper sort of instrumentation, you have to have proper conditions. You may see over time that actually the amount of lithium decreases, depending on what lithium compound you're looking at.
Okay, this is more kind of a specific question. What would be the average interaction volume from EDX, say at the accelerating voltage of 15 kV?
It's dependent on material and density. You can do a Monte Carlo simulation to calculate that. There are some formulas that you can look up for things, references to sort of get an idea of that. Sometimes you'll see charts that'll give you an idea of things. It becomes more complicated when you're dealing with things that are not single elements, so mixtures of things.